Volume Calculations 3. The Cylindrical Shell Method. Example. Find the volume of the solid generated by revolving about the y-axis, the region defined by y greater than or equal to 0 and less than or equal to 3 divided by x cubed, and x between 1 and 3. Now here's the graph of y equals 3 divided by x cubed, and the region of interest between x equals 1 and x equals 3. The solid obtained by revolving the region about the y-axis looks like this. We'll approach the volume calculation by thinking of approximating the solid with cylindrical shells. This animation shows an approximation with 10 cylindrical shells added one after another. Notice how this arrangement corresponds to a midpoint approximation of the revolved region using 10 rectangles. In fact, each shell is the result of revolving about the y-axis a slice of the region that's parallel to the axis, as opposed to a perpendicular slice which would result in a disk or washer. Our job now is to describe the volume of a typical such cylindrical shell, corresponding to a typical slice of the region located at x. Let's observe that the radius of the shell is just x, as it always will be when the axis of revolution is the y-axis. Next, let's describe the height of the shell. That will be the y-coordinate on the curve, which is 3 divided by x cubed. So the volume of the shell, delta V, is approximately equal to circumference, given by 2 pi x, times its height, 3 divided by x cubed, times its thickness, delta x. So we define a volume differential by dV equals 2 pi x times 3 divided by x cubed dx, or 6 pi divided by x squared times dx. Now the volume of the solid is the integral of dV over the interval on the x-axis where the original region lives. So the limits of integration here are x equals 1 to x equals 3. Next we antidifferentiate, obtaining minus 6 pi times x to the minus 1 power, evaluated between 1 and 3, which equals minus 6 pi times 1/3 minus 1, so we have minus 6 pi times negative 2/3, which equals 4 pi. Example. Let R be the region in which y is greater than or equal to x and less than or equal to 4x minus 3x squared. Here's a picture showing the graphs of y equals x and y equals 4x minus 3x squared. The region in which y is between x and 4x minus 3x squared is the region between those graphs where the parabola is above the line. By setting x equal to 4x minus 3x squared and solving for x, it's easy to determine that the graphs intersect at x equals 0 and x equals 1, so the points of intersection are the origin and the point 1, 1. Let's find the volume of the solid obtained by revolving R about the y-axis. Consider a typical slice of the region taken parallel to the y-axis, and notice that the top of such a slice is always on the parabola, and its bottom is always on the line, so its length can be described simply. Revolving that slice about the y-axis produces a typical cylindrical shell among a collection of shells that approximate the solid. Now let's put a picture of the solid to the side and go back to the typical cylindrical shell, which we assume corresponds to a slice of the region located at x. So the radius of the shell is x, and its height is the y-coordinate on the parabola, which is 4x minus 3x squared, minus the y-coordinate on the line, which is x. So the height simplifies to 3x minus 3x squared, or 3 times x minus x squared. So our volume differential dV is the shell's circumference, 2 pi x, times its height, 3 times x minus x squared, times its thickness dx. We'll prepare this for integration by writing it as 6 pi times x squared minus x cubed times dx. So the volume of the solid will be the integral from 0 to 1 of 6 pi times x squared minus x cubed. Now we antidifferentiate and evaluate between 0 and 1, obtaining 6 pi times 1/3 minus 1/4 minus 0, which equals 6 pi times 1/12, or pi over 2. Now let's think for a moment about why the cylindrical shell method was especially appropriate here. Had we chosen to slice the solid horizontally, we would have needed to describe washer volumes, which when located in the lower part of the solid would have an inner radius given by the x-coordinate on the parabola, and outer radius given by the x-coordinate on the line. These would need to be expressed in terms of y. But if the washer were located in the upper part of the solid, its inner radius and its outer radius would both be x-coordinates on the parabola. To obtain these, we would need to solve y equals 4x minus 3x squared for x using the quadratic formula. The solution with the plus sign is the outer radius, and the solution with the minus sign is the inner radius. Now, while all this is not terribly difficult, it is far more complicated than necessary. In fact, it's a bad idea when the cylindrical shell method is so much simpler. One more example. Let R be the region in which x is between y squared over 4 and 2 plus the square root of y. The graph of x equals y squared over 4 is this rightward opening parabola. To see the graph of x equals 2 plus the square root of y, let's first solve for y to obtain y equals x minus 2 quantity squared, whose graph is an upward opening parabola with vertex at 2, 0. But x equals 2 plus square root of y requires x to be greater than or equal to 2, so we have only the right half of that parabola. Now also notice that the square root of y appearing on the right side of the inequality implies that y must be greater than or equal to 0, so our region R is the one shaded here. Also, it's easy to see that the two curves here intersect at 4, 4. Let's find the volume of the solid obtained by revolving R about the x-axis. Here's what the resulting solid looks like. Now let's think about taking a slice of the region parallel to the axis of revolution at height y and revolving that about the axis to form a typical cylindrical shell. Here the thickness of the shell will be dy, so we need to express the shell volume completely in terms of y. Clearly the radius of the shell is y, and its length is the x-coordinate at the right end, which is 2 plus the square root of y, minus the x-coordinate at the left end, which is y squared divided by 4. So our volume differential dV equals shell circumference 2 pi y times width or height 2 plus the square root of y minus y squared over 4 times thickness dy. Let's prepare this for integration by multiplying the y factor through to obtain 2 pi times 2y plus y to the 3/2 power minus y cubed over 4 all times dy. So the volume of the solid will be the integral from y equals 0 to y equals 4 of dV. Now we antidifferentiate and evaluate between 0 and 4, obtaining 2 pi times 16 plus 2/5 times 4 to the 5/2 power, which is 2 to the 5th, or 32, minus 1/16 of 4 to the 4th, which is 256, minus 0. Now notice that 1/16 of 256 is 16, and so the quantity in parentheses is exactly 2/5 times 32, or 64/5, and 2 pi times that is 128/5 times pi. Now let's look at a summary of volumes of solids of revolution. Let's say that we're going to take a region and revolve it around the y-axis, or for that matter, some other vertical axis. If we take a slice of the region that's perpendicular to the axis of rotation and revolve that around the axis, we end up with a typical disk within the solid. We use that disk to write the volume differential that we're going to integrate. The disk has a radius, which we'll call r, and the volume differential corresponding to that disk is dv equals pi times r squared times dy, which we think of as the thickness of the disk. Now, of course, in this case, r would have to be expressed in terms of y. In some situations, rather than disks, we end up with washers when revolving a perpendicular slice of the region about the vertical axis. To write down dv here, we think of the inner radius, which is the radius of the hole in the washer, and an outer radius, capital R, and write dv as pi times capital R squared minus little r squared times dy. Of course, both of these radii must be expressed in terms of the variable y. Now suppose we're going to look at a slice of our region that's parallel to the axis of rotation. When we revolve that slice about our axis, we generate a cylindrical shell, which we use to help us write down the volume differential dv. The shell has a radius, r, as well as a height, h. And so dv is 2 pi r, which we think of as the circumference of the shell, times the height, h, times dx, which here we think of as the thickness of the shell. Notice here that revolution about the y-axis or any other vertical axis results in an integral that's done with respect to x. And of course the radius r and the height h must be expressed in terms of the variable x. Now each of these pictures involves revolving about a vertical axis. Of course, if we revolve around a horizontal axis, we simply treat things in more or less the same way. Slices of the region perpendicular to the x-axis would result in disks or washers and integration with respect to x, while slicing the region horizontally and revolving those slices would give us cylindrical shells, and the integration would be done with respect to y.